there are kind of two different things that can go wrong. The first is computer safety. This is to keep your physical machine safe. For example, if it gets wet, there might be damage to the hardware. If there is some lightning strike, that can also damage the electronic parts of the computer. And there can also be other errors, such as with the software that is not working, and then maybe your data is lost. Or it can also be caused, problems can also be caused by the user themselves. For example, if they delete the wrong file, and yeah, that the hard disk can also simply die and not work anymore. On the other hand, computer security is the protection from attacks. So this is something you can't control, and the company producing the electronics can also not control. Basically, it means that someone can listen to, for example, our meeting, and then, yeah, hear everything we're saying, or they can read your text messages and emails, and that's something you don't want to have, especially for companies that have confidential information in their internal systems. So this needs to be safe. Like, you can lose your identity, and also their malware, such as viruses and Trojans and other sort of software that is meant to, yeah, to harm your computer and your privacy. So for the computer safety thing, you can do backups, you can have multiple layers, for example, of redundancy, so that if one feature fails, there may be another. But for computer security, that's where cryptography comes in handy. So first, an example. If you're on a website, for example, if you're on your school's website, you might have an admission control. The system checks who you are before letting you into the system and to the information, and then access control. So which functions of the software, for example, you can use. So there are a few ways to do that, probably through email or password, and then you also can, on many websites, just click login with Google or Apple or whatever. And another method is, for example, probably on your phone, you're using fingerprint or face ID. And there are also security questions or these CAPTCHA checks that ask you to look at images and decide which one is a bag and which is maybe something else, to test if you're not a bot. And obviously, two-factor identification is very important, especially nowadays. Yeah, when you really need to make sure that it's you and not someone else. Yeah, as I said, probably on your school's internal website, you can you can log in with your student email, and then you get access and can, for example, read the information, but you also need to be authorized. For example, you can probably write news articles for your school's internal intranet, but you can read them. But if you have a staff login, you can make more changes. So you first have to prove your identity, and then you get the permission. So we won't go into detail about these terms, but here you see a basic overview of some malware, but we won't cover them during this webinar. So eavesdropping is basically when someone listens or passively gets access to your data, and for that we need encryption. So if two people, say Alice and Bob, they send each other text messages, they have to make sure that no one else can read it. So cryptology is what helps here. So basically there are two sides: the people that build the systems that encrypt the information, that make sure that nothing can be stolen, and the crypto analyst that tries to break it. And this doesn't have to be a malicious hacker that wants to abuse your information to get money. It can also, this is also an important job, because if you have a system and you don't test it for weaknesses, you don't know if there are any weaknesses. So you have to test it. And nowadays, it's mostly, like, especially in the last 2 or 3 months, AI has been doing a lot of this job, because it has got so capable that it can identify weaknesses in the software that humans haven't noticed, sometimes for decades. And therefore, it's really important that not an everyday person gets access to those capabilities, but the IT people who have to manage the world's critical software, they should have. Okay. There, in this scenario, you have Alice, Bob, and Eve. Alice just wants to try to send a message to Bob, who receives it. But in the meantime, a passive attacker can listen to your conversation and then get access to the data. And this isn't active, so the information just is going, for example, is being transferred through Wi-Fi, and then it's quite like it has, like, there are possible opportunities to get access to the messages. And so you have to make sure that Eve doesn't understand what you're writing in your messages, even if Eve gets it. So this isn't necessarily a malicious hacker. As I already said, crypto analysts, also, that's a job. So you have, for example, the plain text. That's the message that Alice and Bob want to transfer between each other, and it's written in a human language like English that both understand. There's the ciphertext, the transformed language, transformed message, and this is only the status of the message while it is being transferred and travels. And you can uncipher and decipher it. So basically you go from the real message to the ciphertext and back to the plain text. And only Alice and Bob know the method to go from plain text to ciphertext and back again. That's their head start, and that's why they have an advantage. They receive a message they can't read, but they know the method to go back to the original version, but Eve does not. This is obviously not the method being used in modern day cryptography, but it's still an important example to introduce the field. So here is an example of how you could do that. You have a grid with the alphabet. One letter is missing to make it fit into this grid, but you can basically have a letter and then change it to a different, like into a number. For example, party would become P. It is first 3 and then 5. A is 1, 1. R is 4, 2, and so on. Like that's a method. You transform letters into numbers. And this has several advantages. If you see this number code and you don't know this method, you can't read the information. But this is, for example, if you like in a classroom and you want to pass a message around and you don't want the teacher to read it, you you can use that because the teacher probably doesn't know about this method and it is not that important. But in real systems that protect, for example, company data, you have to use something different because someone could find out that this method exists and how it works. Okay. So here is an example. You can already see the solution, but if you have this code, I hope it's correct. You can look, for example, for 3, that would be S, and then you can read STEM2Connect. Like you already see a disadvantage. You can't use numbers in this example, so you can't write STEM2Connect and transform it into this polybios system. So this method is not very safe. But now you can try it and write it. Oh, wait, sorry. I already showed the solution. I should maybe change to the slideshow. I hope you can still see it. Yeah. I think I'll just make a screenshot and then I'll send it in the chat so you can try this example yourself. You can write the solution you get in the chat. So basically, if you need some help, you can try to go to building. For example, you can start with the B. This is here, and then B would become 1, 2, and then the U would become 4, 5, and so on. And if you have the numbers and want to know the word, you can also do it the opposite way around. So you go to 3, 1, which is an L, 1, 5, that is an E, and so on. Okay, I try to show you the solution. So here it is, but it may be that I also made a mistake. But let's don't hope so. So, okay, this is just one method, and there are more methods. I hope you can still see my screen now. Yeah. So this is another method. It is a bit more. It is similar but a bit different. So I show you how it works. For example, if you have the word school, you have to look in the grid where S is. S is here, and then you have to um, look at the you have to look, for example, this is opened upwards. For the S, the C, it is like I show you maybe the solution that's easier. So you can see basically you always take the grid and show like how it looks like. For the H, it would be like this because the grid around the H looks like that. And if it has a point, you also include the point. So this is a very similar system, and this also works for the other way around. You have a word and you want to encipher it. That's the solution if you would encipher the word roller coaster. So what you basically saw now is not a real encryption. It is just something you would also, like children would do if they want to pass on a secret message or something like that. But what is the problem here? It is that you can't, you can't, it is not really secure because if the method, if the safety of a method rests only on keeping the method itself secret, for example, that you transform it with the grid, then it is security by obscurity. So the secret survives not long, and one leak breaks every message ever sent with that method. So this is not what is used in modern day IT security, because it would just mean everyone can basically access your information that knows about the system. So for that, we use, for example, symmetric encrypted systems. This uses a key. So even if everyone knows how the method works, if they don't know the key, they can't get access to the data. For example, only the method is public, so everyone knows how to encrypt something with this method, but the key that Alice and Bob use, or that the service provider like WhatsApp or something like that provides, is secret. And then it is just encrypted and decrypted. Symmetric basically means that the same key is used to lock the message on Alice's side and to unlock the message on Bob's side. So both of them use the same key. The key space measures how how many keys there are in a how many keys there are, many possible keys there are. If there are more possible keys, then the system is much harder to break, especially through brute force. There is a principle called Kerckhoffs's principle that states that the security of a crypto system should also be guaranteed if the method is public, and you just need a secret key. This was already formulated in the 19th century, which shows this wasn't just the case in the computer era. So, for example, if a hacker tries to read your text and knows the method being used, they still need to have the key that was used in this exact system. Monoalphabetic systems are very simple. For example, this one, you have two circles with letters, and you turn the inner one around. For example, A would be is now here, but it should be here in the beginning, and then you measure how far it was turned. For example, here 1, 2, 3, 4, 5. The key is 5 because it has been turned 5 around the inner circle. So basically, if you do that, you can encrypt this word to this and this to this. This is not really secure, as you might guess, because it depends on the combination between the inner circle and the outer circle. While an A doesn't necessarily always have to be a set, for example, it can change, but it can just be 25 other letters, and that's just not enough for a real safe system. So here are some examples, but we don't have to go through them because, as I said, the system isn't really used. So now we'll cover how many keys Cæsar does have. So as you may guess, a letter from the alphabet can be transformed into 25 other letters or stay the same. So there are 26 possible positions of the inner disk. And 26 is very easy to compute. Like a computer can do that in microseconds. So this system is not secure. Brute force method is basically when you go through every possible key that exists, and you try all of them. And if it makes sense, you got the key. The key obviously can change. That's what encryption is all about. But still, 26 is like this system is not secure. For example, you can just try all those things and then eventually you'll get the solution. You can also represent the system as a table where you just shift the lower line by a few positions. For example, the A is originally here, but now you shift it to the 5 positions to the left, and all the others obviously too. This is a bit of a better way to represent the same situation, the same method. So as I said, this method is not good. But what if you, instead of just assigning like rotating the disk and everything is still the same order, but it is just at a different place? What if you don't want that? You can also randomly assign the cipher letters to a plain text letter. It doesn't have to be the A, B, C, D alphabet order. It can also be random. And this improves the system quite a lot. You have now 26 like faculty, which is roughly like, it's a huge number. It's like, if you didn't have covered that in school, here's a brief explanation. This exclamation mark basically means that you multiply this number always with the number that is one smaller than the previous. 26 times 25 times 24 times 23, all the 1-to-1, which gives a very big number. So you'd have to, if you use brute force and you'd say, oh, I want to try all the possible keys that are available for this Caesar plus system, it would take a long time. As you can see here, how many years it would take for a computer to calculate all those different possible keys in the worst case scenario. So probably it could also be that, for example, at the second guess, you get the right key. And that obviously means even this this method that looks quite safe at first can also, like, isn't, like, there is no system that is totally secure, because if it's the second guess, then yeah, the hacker has the information. So do you think, you can write it in the chat, do you think that that this method that I just described is secure? So you can write it in the chat if you want to. I think you have to first, like, I think as you see here, like this huge number, it seems quite safe, but do you have an idea where the flaw could be of this whole system? Okay, if not, I'll show the next slide. So the problem is, even if it is random and there is a huge number of combinations that are possible, you still have the plain text letter, and it is the same, like, it is transformed to a random letter. But if you have an A, for example, and it is a Y in the encrypted text, and then it is always a Y, and you can basically then get information about how often it appears, at what position of the word it appears, and this is the problem with this whole method. So yeah, if you have Mississippi, for example, that has a lot of the same letters, it would just become like the M, which is once, that would, for example, become an L, but then all the P's, which are 2, would be a B, all the S's, which are 4, that would become an I, and then the I's would become an A. So you have the same structure of the word, and there are not so many words with this exact structure. And so that's the problem. And there's another issue, because in a language, there are certain letters that are much more common than others. You see here a representation of the frequency of those letters in a normal text, and therefore, like, you also have combinations of letters that appear often together. And if you have these statistical details about how a language works, you can get to the key that was used for encrypting much easier. So you see that every monoalphabetic crypto system can be broken by frequency analysis. It can't be broken, not all of them can be broken by brute force, which is already a huge advantage. But still, even with this Caesar plus system, it is still possible to look what letters and what combinations of letters appear more frequently in the text. For that, you just need a long text. So it doesn't work if you have just a word. Then this system is really safe. With the Caesar plus method, as you saw, the key space is huge. 26 faculty, which doesn't mean it is secure, but it is secure when it comes to brute force. To make it more secure, you can use polyalphabetic systems instead of monoalphabetic systems. The idea is, if you have a crypto system that is polyalphabetic, you have a fixed key, but the same plain text letter can be transformed into different encrypted letters. So in the examples we saw earlier, if you have a monoalphabetic system, for example, an E is always transformed to an H, and an E is always but it can, in a polyalphabetic, it can be transformed to an H at one point, to an F at another point, maybe again to an H at another point, but it can basically take all the other letters, and so frequency analysis doesn't really work anymore. Vignere is a system for an example for that. So basically, what you see, you have the plain text, for example, a little secret for you, and you use the key house that you just repeat the same word. This is the key, the transformation word, under the plain text. Then you can use a table, and you can see if you have an E in the plain text, or an A in the, let's say rather an A in the plain text, and the key letter corresponding to it is an H, you can look, oh, here is the A. Like on this side, there are the plain text letters, and here are the key letters, and you can see the combination is an H. Okay, this was a bad example. Maybe T or E, no. Or let's say just the example that we saw here. If an E becomes a B, if the plain text letter is an E and the key word that is being used is has a corresponding B, then you get an F in the ciphertext. So as you see, you have multiple E's. Here it is transformed to a C. Here it is transformed to an F. Here it is transformed to a Q. So even if the keyword is always house, you get multiple ways to substitute the letter with each other, and so you can't do the frequency analysis anymore. So I'll send you the screenshot, and you can try to, or maybe that takes a bit too much time. I just show you the solution. I hope you understand this method. Yeah. So now you have not just, you have 26 to the power of n keys. So this depends on the length of the keyword. For example, if you have house, then you have 5 letters in that keyword. So it is n equals 5, so it is 26 to the power of 5. And so the longer the keyword, you can also imagine, instead of one word, you can just use a sentence or a paragraph of text that is always repeated. Or you can also say, maybe I do a text of the exact same length. And the key space gets bigger and bigger with that. And so brute force is not possible anymore. But you may guess, perfect security, even in this example, is not really a thing, because you basically need 4 conditions to have perfect security. So every key has the same length n as the message. So the key really, if you have a text of 200,000 characters, you also need a key that is 200,000 characters long. If you have, like, the key characters have to be random, and every one of them needs to be equally likely. So it can't be that you use a word, because the word represents language, and in language, not every letter appears at the same rate. And the key needs to be different for everything you encrypt. And there are as many possible keys as plain text and a ciphertext. So this would be a very good system, but it isn't used in practice because this is just not feasible, but also not really important. Yeah. I think those were the main things I wanted to share about cryptography. If you have any questions, please write them in the chat. Okay, I see a question. Okay, maybe we can go through some more examples of how this works. I'll send a screenshot in the chat. So for how the method works, you have a keyword. This is what you would see, what you would have here. Here would be the keyword and the corresponding letter, and you would have the plain text. And then you basically write them above the plain text and below the key. And then you look if the plain text has an E, and for example, the keyword that would be below the E was a B, then it would be transformed to an F. So yeah, that's how this system works. And yeah, I think practice would definitely be important for that. So yeah, I can show you also send you this example in the chat, and then you can look at it. It's just that the above table, the table I sent before, isn't complete, and therefore you can't really do the example. Yeah. Are there any more questions? Okay. Okay, a question is there a particular app that does this? So I don't know exactly how this works, but it is embedded in pretty much your operating system, on your phone, on your in your apps. So this is kind of everywhere, but how exactly it works, I don't know. But this is such a key, like encryption is so important for your data to be secure. It has to be kind of in every application, but how it works, I don't know.